Welcome everybody. Exercises for complex numbers part 2. These are exam questions from German universities for first year students of engineering and electrical engineering. We are given this complex number 10 times e to the 13 over 6 times pi times I divided by I minus 2. And you're supposed to find the modulus of this complex number and the imaginary part. Now the easy way would be to bring the denominator into polar form and then calculate this fraction and determine the absolute value and the imaginary part. But as no calculators are allowed in these exams, it's not possible to find the correct angle without, at least I don't know the value for this angle here without a calculator. So we have to go the hard way, which is first bringing the numerator into Cartesian form. This was actually part A of this exam question, but we're doing it in one, and by this we start. Okay, first of all, we write this fraction here in the exponent as 12 over 6 times pi I plus 1 over 6 pi I. And then we use the functional equation of the exponential function and transform the sum in the exponent into a product of two e terms. Now this here is 2 pi I, so this whole expression here is simply 1. And for this expression we use Euler's identity or Euler's formula. This is the cosine of pi over 6 plus I times sine of pi over 6. And these values you must know. This here is 30 degrees. The cosine of 30 degrees is square root of 3 divided by 2. And the sine of 30 degrees is 1/2. So we end up with this expression here, and if I multiply it by 10, we have 5 times square root of 3 plus 5i. And now we can calculate this fraction here. So the numerator looks like this, and now we use the same trick as always. We extend this fraction here with the complex conjugate of the denominator. And here I switched the I and the minus 2 so that it is obvious that I here, the imaginary part, is plus 1. So the complex conjugate of the denominator is minus 2 minus I, and so we extend this fraction here with this 1. So that in the denominator, using the third binomial formula, we end up with the real part squared plus the imaginary part squared. Very important here is plus, because I times I is minus 1. So we end up with a plus sign here. And in the numerator, you actually have to use the distributive law, which gives you these 4 terms. So pairing up the real and the imaginary parts, I obtain this here. And now luckily, all the terms are divisible by 5. And in the end, this here is the Cartesian form of this complex number. Here I switched the order. So the imaginary part now is obvious. This is this here. And for the modulus, I actually have to do the calculation, squaring this plus the square of this and then the square root of the whole expression. This is not hard, but takes a little bit of work. Using the binomial, the second and the first binomial formulas, I end up with this expression. 4 times square root of 3 cancels. And in the end, I end up with 20. I calculated the modulus squared so that I do not have to write the square root all the time. And then the desired absolute value or modulus of z is the square root of 20, which can be written as 2 times square root of 5. Okay, now the next part of this exercise number 5 is very interesting. It looks a bit unusual at first glance. We are given a set m of complex numbers, of non-zero complex numbers, that satisfy that the argument of z to the third power is pi over 2. Remember, the argument is nothing but the angle of the arrow, or the angle in the polar form. And you're supposed to find all the values that the argument of z itself, which lie in this interval, can take. And you should sketch this set M in the complex plane. Okay, a more conventional way to write down this exercise would be find all the solutions of this equation here, pi over 2, because of this, and here z to the third power. And since the length of the arrow is not important, we solve this here for arbitrary radius or length of the arrow on the right side. Now this you should be able to do pretty quickly. So we simply have to use the methods we already know for solving this equation to this question here. Okay, so if z is a solution of this equation here in polar form, actually I should call this here then S, because this is not the same r, then the third power of this expression here is the modulus to the third power times e to the 3 phi I. Because taking e to the phi I to the third power exactly means that we take the argument times 3. So the argument or angle of this expression here clearly is 3 times phi, the initial angle we started with, and this is supposed to be pi over 2. So of course, one solution would be this here divided by 3, so pi over 6 radians or 30 degrees. And now remember, what would you do to solve this equation to find all the solutions? You would multiply one solution with the 3 third roots of unity, meaning that you add 2 pi over 3 or 4 pi over 3 or 6 pi over 3 to this angle here. Okay, if this is not clear, please refer to the first video and look at what we did in exercise number 2. And 6 pi over 3, of course, is 2 pi, so we end up with the first solution here. So these are the solutions we are looking for. So the answer to the first question would be these are the 3 possibilities for arguments of z lying in this interval here. Okay, once you understood this, then sketching this set is simple, because all you have to do is to draw 3 lines under these angles here, and you have to exclude the origin because z is not supposed to be 0. So this here, the first angle pi over 6 corresponds to 30 degrees, and then you simply rotate this line by 120 degrees or 2 pi over 3, and then another rotation of 2 pi over 3 gives you this angle, which all in all is 270 degrees. And then the blue lines together are the set M. And now for any fixed value of S here, you would find 3 solutions of this equation who form together an isosceles triangle. And since S is arbitrary, you get all the endpoints or corner points of such isosceles triangles, which gives you again this figure here. So that's a very nice variation of just simply solving this equation here, because the modulus is arbitrary. Okay, next exercise, number 6a. You are supposed to sketch this set of complex numbers in the complex plane. All the complex numbers satisfying this equation, that the absolute value of z minus 2i is the same as the absolute value of z plus 2. And you also should write all the solutions or all the elements of this set here in this form. So here it should be apparent that this is a line in the complex plane. Okay, to really see what's happening here, if you haven't seen this before, it's important to write this here slightly different. Z plus 2 is the same as z minus minus 2. And now we have here something of the form z minus another complex number w1. And this is simply the distance between the points capital Z corresponding to this complex number and the point capital W1 corresponding to this complex number, -2/0. Yeah, this here is the complex number W1, simply -2. And this here is the complex number W2, leading from the origin to the point capital W2. And now this simply reads, we're looking for all the points capital Z that have the same distance from this point and from this point. And these points, of course, lie on the perpendicular bisector of this line here, W1, W2. Now, if you're seeing an equation of this form for the first time, this actually is pretty hard, especially if you're not able to see this little trick here. So that's the solution to the first part. As I already said, the perpendicular bisector, in German Mittelsenkrechte, of these 2 points here, or of this line connecting these 2 points. And now to write this here in this parameterized form, you simply should think about straight lines in Euclidean 3 space that you already know from math. So as this vector here, we can take the origin, 0, and then we take this vector here, for example, or this vector, doesn't matter. So this angle here clearly is pi/4 or 45 degrees. So we have I, and because we're going down, we have to take minus pi/4 times I here in this polar form. And since it isn't specified that this angle must lie between 0 and 2 pi, we can just leave it like that, or you can add 2 pi if you want to. The length of this vector doesn't matter at all because we have here the real parameter, I'm not sure, parameter t, which can take all the real values. So this here would be the desired required form of all the points lying here on this straight line. So in German, this here would be the Stützvektor and this would be the Richtungsvektor, the directional vector. And then you have the standard form of a straight line. Usually you are used to r to the third or r3, Euclidean 3 space, but here we work in the complex numbers, which as I said is nothing but Euclidean 2 space. Okay, part B of this last exercise is to solve this equation in the complex numbers. Now this we already did in principle in exercise number 2, so I'm only giving you some hints and the solutions. First of all, you have to find the standard Cartesian form of the right-hand side by extending this fraction with the complex conjugate, 1 minus 4i. If you do this, you end up with this. Then you have to transform this into polar form. But the angle of this arrow is simply pi/4, 45 degrees, and the length of this arrow is square root of 2. So this here is the right-hand side in polar form. If you wish, you could write this also as square root of 8 times e to the pi/4i. So then one solution is obtained by taking directly the third root of this here, of the length, so third root of square root of 8, and dividing this angle by 3, so you end up with pi/12 times I. Now this here is the sixth root of 8. 8 is 2 to the third power, so you end up with 2 to the 1/2 or square root of 2 times e to the pi/12 times I. So in my book I call this first solution W for German Wurzel. In the solutions to this exercise sheet I call it Z sub 0 or Z0 so that there's no confusion. I wanted to show you these two notations. It doesn't matter at all, you can call this whatever you want. And then the same trick as in exercise number 2. To obtain all the solutions, you simply multiply this one solution with all the third roots of unity. K running from 1 to 3 or from 0 to 2, doesn't matter. And these here are e to the 2 pi over 3 times I, and this here times k. So the third root of unity in this notation would be e to the 2 pi I, so simply 1. So the third solution, z sub 3, would be our initial w, or z naught. And I'm leaving out the rest, the details, just to spell it out. And you're not supposed to find the Cartesian forms, because for that you would have to know what the cosine and sine of this angle here is, and we do not know that without calculator. Okay, now the last part of this exam question was to find the real part and the imaginary part for this guy here. N is any natural number, and you have the sum of these two fractions of 1 plus I divided by 1 minus I, two different powers, n plus 1 and n. Students of mine do not have to worry, I will not ask this in my exam, except for extra credits. But it's a very nice challenge and exercise for you at home to at least try to find this. So here are the results. Please try on your own. In both cases, this number here is a real number, so the imaginary parts vanish. For an even exponent, so n is of the form 2 times k, k any natural number, the real part, or the number itself, is simply 2 times minus 1 to the kth power, k being this number. And in the case that n is an odd number, so 2k plus 1, k is now natural or 0, because you want the 1, so 0 is allowed for k here, not here. The real part of this number, or the number itself, is 2 times minus 1 to the k plus 1. All right, that's it from me. That actually will be my last video, my last math video in 2021, and maybe ever, I haven't decided yet. It was a ton of fun producing these videos, of course also a lot of work. Thanks for watching, thanks for your support, and maybe I will see you again on this channel or elsewhere. No, that's stupid. So, thank you very much for watching and for your support, and to cite Michael Penn, that's a good place to stop.